Hello everyone, welcome to the fifth week of our course on AI for Earth observation. In this course, so far, we have talked about the basic application areas of Earth observation. Why should we study AI for Earth observation in the introductory week? Following this, in the second week of the course, we also discussed a bit about traditional machine learning paradigms that were used before the era of deep learning. From week 3 onwards, we have been discussing deep learning. We started with some basic classification architectures. We have talked about different learning paradigms. We have talked about self-supervised learning, generative adversarial network. So far, we have got a bit basic idea of how to use deep learning for semantic segmentation, for classification. And we have got a bit idea about the architectures. We have got idea about different learning paradigms. With this, now in this week, we will be focusing our discussion on SAR images, which is indeed one of the most important sensor in modern Earth observation. We have introduced SAR images to some extent in our introductory weeks. However, we will take forward this discussion. We will start today's lecture by discussing again a bit about the basics of the SAR images, and then eventually we will discuss different learning tasks or different SAR image plus deep learning tasks or research paradigms that are popular in the literature. In this week, we'll also introduce a bit of architectures as well, like object detection architectures, which we have not discussed before. We will discuss in this week. Indeed, object detection is one of the important tasks in SAR image analysis, hence we have kept this for this week. Similarly, we'll talk a bit about complex deep networks as well. Indeed, complex deep networks is used in the context of SAR image analysis, and hence this discussion we'll be doing in this week. So with this background, let us go ahead with today's lecture, where we are more interested to understand the SAR images and different tasks and like how AI or deep learning is playing a role in this. So SAR, synthetic aperture radar, this is an active sensor that transmits and receives its own signal. It produces images using the radar backscatter It's widely used for Earth observation under all weather conditions. And this is not the only reason I will say, rather, this is one of the primary reasons that SAR image is popular in Earth observation. Whereas the optical images, they cannot be used in the presence of clouds and other weather conditions. The SAR indeed we can use in several such situations where we would not be able to use optical images. So, talking a bit about the optical images versus the SAR images, or rather optical sensors versus SAR sensor. Optical sensors depend on sunlight and are affected by clouds. SAR, on the other hand, is an active sensor. It transmits its own microwave signal and can acquire images both during the day and night time. And as we have already mentioned, that microwaves can penetrate clouds, hence making it useful in special seasons like monsoon and all, when optical images become quite unusable due to such constraints. So, to understand why we are interested in SAR images, indeed, we have already discussed that it can penetrate clouds. It's less affected by atmospheric scattering. Adding to all this, certain bands of SAR, which we have briefly mentioned before in our introductory weeks, and in this lecture we'll again mention. So what happens is that certain bands of SAR also penetrate vegetation, and this makes it useful for certain applications for which otherwise we cannot just use multispectral images. SAR is an active remote sensing system, thus sending the microwave pulses towards the Earth's surface, and each pixel represents radar backscatter rather than reflected sunlight. Indeed, the way that SAR imaging system is different from our optical multispectral images, this makes it also in some way challenging to analyze. And more specifically, the visual saliency in the SAR images, you cannot just see a SAR image and, unless you have really lot of experience of working with SAR images, you would not just look at a SAR image and you would guess that, okay, what are you looking at? Unlike, optical images where, of course, the visible bands we look at and we can make a guess. Even if you're not looking at RGB bands, even if you're looking at, let's say, NIR bands, even then probably NIR bands, if we make a false color composition with the multispectral images, even then, most of the time we can make reasonable guess. With the SAR, this is not that straightforward or trivial. The side-looking geometry of SAR also contributes to complexity. Indeed, we'll see there are architectures or there are research works which just try to account for the side-looking geometry of the SAR, the looking angle of the SAR sensor. So what happens is that SAR observes the Earth from the side rather than from directly, like rather than looking directly below. So the area that is directly beneath the satellite carrying the sensor, that is generally not imaged. Geometry strongly influences object appearances in the SAR images. We also need to note in this context that if we talk about the range, that is the direction perpendicular to flight direction, and azimuth along the flight direction, the resolution of SAR is defined generally separately in the both directions. So this is also unique property which we don't need to face when we are talking about what is world multispectral images. So to understand backscatter a bit better, here are a few cases. Of course, this is just like really few cases, and then like there can be many other variations. So what happens is that the smooth surfaces, as an example, calm water, they reflect energy away from the sensor, and thus they appear dark. So often, if our task is to just detect enough such calm water, we can simply put a threshold and detect. Rough surfaces scatter energy in many directions and often appear comparatively brighter. So one thing I would say is similar in some sense to our discussions related to multispectral optical images as well, that at the end, when we think about analyzing urban area, again, the complexity is quite strong even in the SAR images. So we will, like when we'll discuss subsequently the applications, one of the application lectures in the later weeks, probably week 9. So one of the lectures we have dedicated entirely to discussing urban applications, and there we'll discuss in more details like how often the urban applications are spatially complex. So complexity itself can be like in different along that different dimension. Urban applications are spatially complex. So no matter if we are talking about multispectral images or we are talking about SAR images. Vertical urban structures typically reflect signals of the ground and back, and thus appear bright. Different like interesting phenomenon actually happened in such urban areas with buildings of different heights. So the factors affecting backscatter include surface roughness, moisture content, dielectric constant, and the sensor wavelength and polarization. So the sensor polarization now we'll talk a bit more in this lecture later. And these factors that affect the backscatter, they indeed also decide what kind of application we can use SAR images for, whether we can use, let's say, for moisture mapping, soil moisture mapping or not. So this all gets decided by these properties. Geometric distortions is indeed very dominant in the SAR images. There are SAR-specific geometric distortions such as layover, foreshortening, and shadow. So we'll not go into the details of these distortions and all. If you are interested specifically in the SAR image analysis, you can always read it up from other sources. However, we have to understand, this all indeed often impact how we design our architectures. And we'll see some use case, especially when we discuss the urban applications. So talking a bit about layover very briefly, what happens is that top of the tall object appears before the base, and this is common in the tall buildings. Speckle noise is another very important factor in the SAR image analysis. We'll discuss speckle noise in a bit more details, or rather not speckle noise, rather how to deal with speckle noise using DL in one of the subsequent lectures of this week. Indeed, such preprocessing for speckle noise is often part of SAR image processing pipeline. SAR images contain grainy appearance for the speckle. Speckle, interestingly enough, is not additive noise, rather this is multiplicative in nature. And as I mentioned, that filtering methods, which today's date can be based on deep learning, they are often applied before further SAR image processing, and this is what we'll study later in this week in one of the lecture. So why is SAR valuable in Earth observation? As I already mentioned, that it works in cloudy and nighttime conditions. So this makes it really useful for particular application scenarios. I remember specifically one example when the Ukraine conflict started in 2022. We were trying to look over a particular area which was strongly impacted by this conflict. And after the conflict started, for several weeks, for this area, Sentinel-2 optical images were not available in usable condition, whereas SAR images, SAR Sentinel-1 images were of course available. So this is also something I had mentioned already, that it's sensitive to surface roughness and moisture. It can penetrate through the vegetation canopies depending on the band. We think about the urban applications. If you're talking about say a destroyed building, completely destroyed building, of course you can also use optical images. Whereas when we think about partially destroyed buildings, often it has been seen that SAR backscatter, that is more, or rather I would say SAR plus deep learning pipeline, that is more useful rather than optical images plus deep learning pipeline. So coming to the SAR bands, we have X band, which provides high resolution imaging. It helps in urban mapping. Interpretation wise, in a way, you can think about this is probably something which shows properties closest to the multispectral optical images that we work with. C band helps in land cover mapping, flood mapping, agriculture. S band helps in land cover mapping, agriculture. L band helps in forest structure, biomass estimation. P band helps in deep vegetation penetration, subsurface studies. So with this, like these different bands applications, the dominant applications that I have listed here, from this, probably it's not that difficult to guess which bands are more penetrating, like I mentioned before, right? Like some of them penetrate the vegetation and all. So which bands are satisfying those properties and which bands are not so much satisfying that property. Polarization is another very important aspect to be considered when talking about SAR image analysis. Radar waves are electromagnetic waves and can be transmitted and received with different polarizations. Interestingly enough, different land cover types interact differently with such different polarizations. Thus, polarization can provide additional information for analysis. So, talking a bit about X-band. X-band images are mostly like, since they're high resolution, they're mostly commercial. Some examples include TerraSAR-X, Cosmos SkyMed. Sentinel-1 is freely available from European Space Agency as part of the Copernicus program, and this is the most dominantly used in academic research, since it's freely available, of course. I mean, not just freely available, also it's a nicely C-band which shows, I mean, it's not as penetrating or it's not that high resolution, but it, I will say, like shows like a balance of properties. Sentinel-1 C-band submission, this can have revisit periods, actual revisit intervals. It has varied over the time for Sentinel-1 between 16 and 12 days, depending on the availability of the Sentinel-1A, 1B, 1C, and now there is also 1D. So this, depending on the satellites, the revisit period has varied or will vary in the future. Sentinel-1 comes in single look complex format, where we have the backscatter and the phase information. Indeed, phase information is one of the important aspects to be considered in SAR image analysis. And as we already mentioned that we will discuss towards the end of this week about complex deep networks. We also have ground range detector, which doesn't come with phase information. And Sentinel-1 also comes with different acquisition modes, such as interferometric, wide swath, or strict map. NICER also deserves mention, which is a joint mission conducted by ISRO and NASA. It's quite recent, NICER. It carries, interestingly, both L and S band SAR systems. So it's carrying at the same time two different bands. That's a very interesting aspect. So to summarize about these missions and all, here are a few popular missions which in the scientific literature you will often face, like Sentinel-1 C-band operated by the European Space Agency, TerraSAR-X X-band operated by DLR, that's the German Space Agency, Cosmo X-band operated by Italy, NICER L+S operated by NASA and ISRO. NICER is, as I said, is quite recent, so you will not see like a huge number of research works on this, but this is like something which will be explored significantly in the upcoming years. And this is also something in the Indian context it makes interesting right now to talk about the SAR images. I'm quite sure with nice and something interesting about this is that this is since not just a ISRO mission, it's ISRO plus NASA. So I mean this plus as it's providing to, it's not just about the space agency, it's information that it's carrying. So it's providing two different bands. So I'm quite sure that this will become data source for many research works in the years to come, that is starting from like I'm talking about in 2026. So yeah, years following 2026. So now setting the background for deep learning for SAR. Deep learning learns features directly from the SAR images and thus reduces dependence on handcrafted texture descriptors. And indeed, I mean, these texture descriptors and all, they were framed otherwise in the context of the optical images. So SAR images, I mean, as I said, that visual saliency is indeed not so strong. And whenever you don't have the visual saliency, when like these handcrafted features, like Hadalix texture features and all, they all have also come from like one thing, that is observation, right? If you have to like create a new formula and you say that okay, like this probably will work, you are handcrafting the formula, I mean, right? This will come only from your observation, right? So SAR image, which is not so easy to like visually understand, it's also very clear that automatically it's not so easy to like design handcrafted features which works well on the SAR images. So in this context, deep learning indeed is providing the mechanism for also learning the feature, which is really good. I mean, optical images also it was useful, but SAR images, I will say, like it's in some way even more useful, that it enables end-to-end learning for different given tasks. However, we have to also understand the challenges for deep learning in SAR image analysis. We have already talked about like how limited annotated data sets, this is a very important challenging aspect. And this is something becomes even more of an issue when we talk about in the context of SAR images, right? Like in the context of the SAR images that providing annotation, creating such annotated images, this is even difficult. And when we talk about actually like dense tasks, this is even much more difficult, right? Dense tasks like semantic segmentation, this becomes really difficult. This is the reason you'll see like even on today's date, there are like really few data sets which provides like SAR annotations for semantic segmentation or object detection. I'm not saying that there are none, but there's very few. The variation within the SAR data itself, this is also, of course, something to be noted. So one particular band might not work well for the another particular band. And also there is, let's say, like differences with polarization and all. So this brings us to, like the problem domain of the domain adaptation or domain generalization. This is something we will subsequently study in, I think, week 7. So this is a very important aspect in the case of the SAR image analysis, and the lack of visual saliency. I mean, this has already been included in my discussion when talking about the previous 2 points. So what are the common deep learning tasks in SAR? This includes image despeckling. So as I mentioned, like image despeckling, this is often included as a pre-processing task. And this can be done using deep learning, but often people also just use as some traditional filters. Since despeckling literature, this was indeed already like quite vast even before the deep learning era. So there were like filters designed for this. Image classification, just like in the case of the optical images. Semantic segmentation as well as dense degradation, like let's say you're trying to estimate biomass. Of course, this will depend on the appropriate type of input. Object detection. Indeed, object detection is a very important aspect in the SAR image analysis. You will see like more scientific literature dedicated to SAR object detection rather than SAR semantic segmentation. So there are like, these are written generally in the context of very specific target detection, like sheep. This is one of the important area. Change detection is a very important area. Change detection is something which will go in details in one of the subsequent weeks. Indeed, I mean, this like combining the optical and the SAR images, this leads to important problem scenarios in change detection, as well as like any other like SAR optical joint learning fusion talks. SAR image classification. The question that we probably ask ourselves is that, do we need any pre-processing before such SAR image classification? The answer we have kind of given right already before. Like we talked about how despeckling can be a possible step. So then the question arises that what about the applicability of pre-trained encoder available on the optical images? Like, can we use such an encoder which was previously trained on optical images and then like tune on the SAR images, or directly apply on the SAR images? The answer is for sure no, right? Then the question is like, okay, like can we tune it? Tune, interestingly enough, of course, we'll discuss more this week, and also actually this discussion will come back a bit towards the very end of this course when we talk about multi-sensor foundation models. So indeed, in some cases, it has been found that, okay, you can fine tune. So depending on the situation, you can actually fine tune from the optical images datasets, or you can also train from scratch. The other question that probably one would like to ask is that, are the existing architectures applicable? Again, the answer is, there is no yes or no answer. It depends exactly what you are trying to do. Do you want to include the phase information or not? And the answer is like this, like you can actually use the existing architectures as it is also, but you can also design for very specifics for the SAR image analysis as well. So SAR semantic segmentation, right? This, in this case, the getting annotated data is even more challenging. In comparison to classification, for sure, you can still get, like, let's say, given images, given chips of like 64x64, you can, or 224x224, whichever it is, you probably can provide just one label per image. That's not that challenging, but semantic segmentation label we have discussed before. It's very much challenging, more challenging, and in case of SAR images, it's even more so, right? And how to address this? We will, something too important to ask ourselves, and this is probably too early to ask this question, but still let us just, pose this question at this moment, and towards the end of this course, not this week, I'm talking about towards the end of this course, sometime you will get some answer. I'm not saying exact answer, because there is no exact answer at all to such research questions. But yeah, so let me go ahead with the question, right? The question is like this, that we can use in the era of the foundation models and all, there are certain models which helps us in zero shot semantic segmentation. Can we also use them for SAR? So not necessarily zero shot, like let's say, like given few examples, these few examples can be in the form of few clicks, okay, few points that you provide, the user provides. Can those be also used for SAR? in that case, if they can be used, maybe the semantic segmentation annotation process could be made much faster. So here is one possibility which we will also expand a bit in this week itself. That is feature distillation. So what happens is that often, let's say like we first train a model on the optical images, and then what we can do is we can freeze the above model, okay? Then we can train, like now let's say our target is to train a model on SAR images. Now what you can do is the SAR model, this we can task to both predict the segmentation labels, okay, so on whatever data, like some annotated data is available, let's say, and at the same time we can ask it to produce, okay, so using some kind of distribution laws we can ask it to produce a similar feature as generated by the optical model. Of course, in this case, feature generated by the optical model on the optical images, which captures similar kind of distribution, similar kind of area, okay. So this is one possible idea. This has been used in different forms. Feature distillation has been used in different forms in different works related to SAR image analysis. Dense prediction as regression. So one is semantic segmentation itself, where for each pixel we are trying to get a label, right? But also the other variation is that, okay, we are, instead of like a particular label, we are trying to get a regression. So as I mentioned, like the biomass estimation as an example. So again, here the aspects to be considered, one is very important, one is input itself. Specific types of SAR data that will only work well for this kind of applications. Probably you cannot just use X band, like SAR image and say that, okay, I want to do biomass estimation. And accordingly, the output, will need to think about the output layer, and you will need to think about, in such case, the loss function. Okay, the loss function will change, right? Since we're now doing regression. So object detection in SAR, as I mentioned, that this is a very important problem area. And as I have discussed already, that indeed object detection is something that we will be discussing more details this week. In fact, the next lecture itself. Ship detection, as I mentioned already, like this is something that is actually like a lot of scientific work around that. Building detection is also another interesting problem. SAR change detection, like for disaster monitoring, it's very useful. Like as I have also might have mentioned in the introductory lectures, that let's think about an earthquake, and once the earthquake has happened, you cannot really wait just for a good optical image. So in such case, you need to actually work around with like different kind of combinations, like optical pre-change and SAR post-change. For pre-change, you can characterize using both optical and SAR image, whereas post-change is characterized using the only first available SAR image. So as I said, also like this change detection is something we'll be discussing in more details in one of the subsequent weeks. So let us just like very quickly at this point go through like how does a SAR supervised change pipeline will look like. It will comprise of shared feature extraction, that is from the pre-change and the post-change image, feature extraction from the both, feature comparison, feature fusion, and then pixel-wise change detection. So this, I was talking more in the single sensor scenario, where let's say the pre-change and the post-change both are SAR images, or it could have been both optical images. But rather than mere SAR CD, like mere pre-change SAR, post-change SAR, if we formulated this as like the multi-sensor scenario, the scenarios that I just also discussed a minute ago, in that case, how will the architectures vary? So this is also something very important aspect, but this is not something we will go so much details this week, rather in one of the subsequent weeks. So at this point, let us think about some common themes around SAR and deep learning research. One common theme is how to benefit from the labeled optical images. So some kind of feature knowledge distillation, some kind of domain adaptation. So there are like research work around this theme. And around the same theme, there is also another problem statement, that is how to rather benefit from, let's say, labeled or another type of SAR images. So it's not always the case that, okay, you just have like, optical image data set and you want to benefit from this. Often the problem is also like this, that let's say you have actually a SAR data set, but this SAR data set is in context of a specific type of, like, let's say, X-band SAR data set you have, whereas you want to design a model for C-band SAR, and for this you don't have a labeled data set. So can you also benefit from this labeled data set, labeled X-band SAR data set, to train a model for C-band SAR data set? The answer is yes, in the similar direction of domain adaptation or knowledge distillation. Similarly, another theme is how SAR can actually complement the optical based analysis, right? So this is what I already mentioned in the context of the change detection, where let's say like we have optical images as well as, like, let's say we also have the SAR images, and how this is like complementing. Common theme of the research, which is actually very specific to SAR, is designing architectures that exploit the specific properties of the SAR. So one such property is, let's say, the phase, right? And I already mentioned, like, in this context, we'll be studying complex deep networks. Similarly, like another example would be like looking angle. Can we exploit the looking angle? We mentioned, right, that looking angle is a very important aspect. So not even, complex deep learning, like even in our usual architecture itself, like can we somehow fuse this looking angle as an additional information? Another theme is around the generative models. So again, I mean, generation of the SAR data, or like, let's say, transcoding of the SAR data to optical data. So this kind of problems are very popular in the Earth observation. And indeed, with the rise of the diffusion models, of course, this is something even more relevant today in 2026. Another common theme is also around the explainability and the physics guided models. So this is not a theme we'll be delving so much deep into, but this is also something interesting, like, since especially, like, as I said, that SAR images, I mean, they're not visually salient, so it's even more important to understand, like, okay, why the prediction that we got for, like, the specific prediction that we got for a particular SAR input. And interestingly enough, also, like, like by use of the joint, like, multi-sensor inputs, like optical and the SAR combined inputs, often interesting uncertainty aspects can also be designed. Similarly, the physics guided model, this is also something very relevant in the context of SAR image analysis. So with this background, what we'll do is, we will, in the next couple of lectures, we'll talk about the object detection, and we'll discuss, like, the general object detection architecture, which is of course applicable for the SAR images, but also applicable for other images as well. But we'll also take up the examples specific to the SAR image object detection. And following these, then we will spend another couple of lectures talking about how different architectures have been built, or how different, like, models have been built around these common themes that we have discussed so far. in today's lecture. So with this, I will stop here. Thank you.